Hello everyone, welcome back. In this video, we'll be discussing about the last problem of yesterday's biweekly contest. Find the maximum sum of node values. The problem is very interesting because it is one of those problems which can be solved both using dynamic programming and using greedy as well. In this video, we'll be discussing about both the solutions from scratch. If you are here just to watch one of the approaches, all the timestamps will be there in the description down below. Feel free to move to the section you like. Having said that, I would strongly encourage you to watch both the sections because both of them can teach you a thing or two. So let's get started. The problem states that you are given a undirected tree with n nodes numbered from 0 to n minus 1. You are given all the edges of the tree, and you are also given a positive integer k, and each node has a value which is denoted by nums of I. Your job is to maximize the sum of value of all the nodes, and you have one operations with you which you can apply any number of times. So for example, if there is an edge u comma v, you can apply an operation on this edge which will make nums of u to nums of u's or k and nums of v to nums of v's or k. So you can apply this operation as many times as you want, and finally you would want the sum of all the nodes to be maximum possible. So let's take an example. Let's say this is the tree. So there are two nodes 0, 1 and 0, 2. So 0, 1 and 0, 2. The values of the nodes are 1 to 1. So value of 0 is 1, value of 1 is 2, and value of 2 is 1. K is 3. So if you see, the current sum is 1 plus 2 plus 1, which is 4. But you can do better. How? If you apply the operations here. If you apply the operation here, the value of this node will become the previous value zor k, which is 1 zor 3, which is 2, and similarly the value of this node will become previous value zor k. So previous value was 1, zor k or zor 3 is 2. So the value of 0 will change to 2, value of 2 will change to 2. So the final array would become 2 to 2. And if you do the sum now, 2 plus 2 plus 2 is 6, which is greater than the sum before. So this is better sum, but you can't do better than this. So no matter how much operations you apply from here after, you will not be able to get a sum of greater than 6, and hence the answer here is 6. So hope the problem statement is clear. Now how to solve this? So there are two approaches in general. First, you take the usual path with trees, that is you solve the problem for a simplest tree, you see how to merge the values of subtrees and figure out the value of root. That's the usual way. Often it leads to a dynamic programming solution or simple recursive solution which you can memorize to make it dynamic programming solution. Second approach in this case is there is an operation jor. So if you apply the same operation twice, or if you apply the operation on u comma v twice, you will end up having the same value again. Whatever nums of u was, you will have the same value. So with this observation, you can say, okay, at the end, I know my state would be either I will be applying the operation on an integer or I will not apply the operation on an integer. So I need to find the optimal subset of numbers on which I am applying the operation, and if I am able to do so efficiently, the problem is solved. So that's the two approaches. Let's start with the first one, and the second one we will discuss afterwards. So the first one is you start with the simplest tree. So simplest tree is a tree with one node. The value of this node is 3. So what is the maximum sum you can have? There is no edge. Because there is no edge, you can't apply any operation. Because you can't apply any operation, this is the maximum value. So the maximum value of this is 3. Good. Now this is the tree. First node has value, root node has value 3. The child nodes are value 1 and 1. So this is the second most simplest tree you can imagine, right? Now in this case, what is the total sum you can have? So one of the ways is to actually say, okay, I can apply the operation here, or I may not apply the operation here. Similarly, I can apply the operation here, or I may not apply the operation here. So every edge, I have two choices, either to apply or not to apply. So in total, I will have 2 power n combinations, because number of edge in the tree is n minus 1. So overall, I will be having 2 power n number of combinations, and whichever give me the maximum, that I will take that as the answer. So that's the brute force manner, but obviously this will not pass because the value of n is very huge, 10 power 4, 2 into 10 power 4. So we have to optimize this. Now how to optimize this? more often than not, in these kind of scenarios, you can divide the problem into a sub problem. So in this case, you can say, okay, what is the optimal value for this subtree? What is the optimal value for this subtree? Based on these two values, I can figure out the value of this entire tree, right? So that's the usual way in which you approach these kind of problems. So in this case, optimal value of this subtree is actually dependent on whether you have taken this edge or you have not taken this edge, right? So let's figure out the optimal value of the subtree in both the scenarios. If you have taken this edge, what is the optimal value of the subtree? If you have not taken this edge, what is the optimal value of the subtree? So in this case, let's focus on if you have taken this edge. If you have taken this edge, also let's assume that k is 3 for simplicity. So every node value is either 0, 1, 2 or 3, so that at the end you will get 0, 1, 2 or 3 itself after XORing, right? So this is just for simplicity. So the question is, if I have taken this edge, what is the maximum value in this subtree, or maximum sum of all the nodes in this subtree? So if you have taken this edge, this value would have become 1 XOR 3, which is 2. So the maximum value of this entire subtree is 2 itself, because there is just one node which has a value of 2. If you have not taken this edge, then what is the maximum value? Then this value would remain 1, and there is no other edge afterwards, so you can't change the value of this node, and hence the value will remain 1. So this is the two scenarios for this particular subtree. If you have taken, this is the maximum value. If you have not taken, this is the maximum value. Similarly, if you do the same thing here, you will get 2, 1 again, right? So if you have taken this edge, the maximum value of this entire subtree is 2. If you have not taken this edge, the maximum value of this entire subtree is 1. Now, what is the total sum or total possible maximum sum? So total possible maximum sum would be only this node is remaining. So for this node, again, there are two choices you have. Either at the end you will be applying an operation here, or you will not apply the operation here. For example, if you apply the operation twice, let's say, so in this case this will cancel each other and the final value would remain 3, right? So in essence, either you will apply the operation or will not apply the operation. So if you apply the operation, this will become 0. If you don't apply the operation on this node, this will remain 3, right? Now applying the operation here actually depend on whether you have applied operation on any of the adjacent edges. So we'll come to that, but these are the two values you can have, right? Now what is the maximum possible sum? Maximum possible sum is take the maximum one from here, take the maximum one from here, and take the maximum one from here. So maximum possible sum is 7, right? Now can you, or is it possible? So this depends on what you have taken. So see, you have taken this one here, that is, you have said that I have taken a edge. Similarly, you have taken this one here, that is also saying that I have taken this edge. So in total you have taken 2 edge from here, right? And because you have taken 2 edge from here, in essence this node is not changing at all, right? And because this node is not changing at all, you can take this value, that is, what is the value in which you don't have any operation, or if you don't change the value of this node. So in essence, we have taken this this and this, which is possible, or these three are compatible with each other, because if you take these two here, you will be taking 2 edges and this node will remain as it is, that is, it will have the value 3. So you can get best possible sum here, and hence the answer here is 7. That's good. Let's talk about a similar structure with a different value. In this case, if you take the same approach, what is the maximum value if you take this edge? What is the maximum value if you don't take this edge? Similarly, what is the maximum value if you take this edge? And what is the maximum value if you don't take this edge? So if you take this edge, the maximum value is 1. If you don't take this edge, the maximum value is 2. In this case, if you take this edge, the maximum value is 2. If you don't take this edge, the maximum value is 1. Now similarly for this one, there are 2 values. If you apply the operation here, you will have 0. If you don't apply the operation here, you will have 3. Now what is the best possible sum? Best possible sum is again to take 2 from here, take 2 from here, and take 3 from here, right? So in total, you have the best possible sum as 7, right? Now, is 7 possible or is 7 feasible? So the answer in this case is no. Why? Because here you are saying I will not apply the operation, right? So you are not applying any operation. Here you are saying I will apply the operation. So in total, across all the edges, you are applying the operation one time. Now, because you are applying the operation one time, it is mandatory for you to change this value, and if you change this value, this will become 0. So if you take 2 and 2 from here, you will have to take 0 from here. So in total, you will have a sum of 4, right? But can you do better? So you have taken the best choices among all of them, right? Now you have other possibilities as well. For example, you may say, okay, I will keep this as it is and I will compromise on some of these, or you will say, okay, whatever I have get is best. So how you will decide? That actually based on which option will give you or will lose you minimum possible value. So total possible sum, maximum value sum is 7. Now whichever option will help you remove minimum possible value is your favorite option, right? Or is the best option you have. Now in this case, how to figure out that? So if you take 3 instead of 0, you will be losing total sum of 3, right? Similarly, if you take 1 instead of 2, you will be losing a total sum of 1. In this case as well, if you take 1 instead of 2, you will be losing a total value of 1. Now the claim is you can have any one of these differences and everything will still hold true. So currently you have total sum of 7. Now 7 you have seen is not possible, because you are saying that you will take this one and this one for 7. Now if you take these 3 things across, you are applying the operation one time here, so this has to change, and this you can't take 3 here. So 7 is not feasible. Now the claim is if you compromise in any one of these, your answer will be feasible. And if that's the case, like how that is the case, we will come to that. But if you compromise on any one of these, if the answer is feasible, then which one you will compromise? Answer is the minimum one. From this 1 and 3, I will take the minimum one and I will say I will compromise that one. So in this case, you will say, okay, I will compromise the minimum one, which is 1. So the maximum value is possible here is 6. Now the question is how I am saying that if I will not, or compromising any one of them will make the answer feasible. Okay, so the answer is in the fact that if you compromise here, that means that you are saying I will take the value here. In that case, you don't need to compromise here, because whatever you have taken would remain as it is, right? Similarly, if you compromise here, that means you are saying that I will not. Previously you are saying that you will take this edge, now you are saying okay, I will not take this edge. So in that case, again, if you see, you are not taking the edge across these two, so overall you are taking 0 edges. So this node, the value of this node will stay as it is, so you can still take 3, right? So overall it's basically how many operations you are applying. If it is odd, you have to change this, and if changing this is the one that is giving you the maximum value, well and good. If that's not the one that is giving you maximum value, then just change the one which is giving you or which is leading to the minimum possible avoidance. So in this case, 1 was the minimum possible loss that we can have. So overall we can have a total sum of 6, right? So finally, let's try over this tree as well before we move on to a bigger example. So we need to find the maximum value here. Again, I will figure out what is the maximum possible sum if I take this node or don't take this node. So the value would be 1, 2. If you take this node, the value will become 2 or 3, which is 1. If you don't take this node, the value will remain 2. Similarly, if you take this node, the value will become 2, 1. If you take this node, the value would be 2. Don't take this node, the value will be 1. Take this node, the value is 2. If you don't take, the value is 1. If you apply the operation here, the value would become 3. If you don't apply, the value will become 0. So let's take the best possible choice again, 2, 2, 2, 2 and 3. So in total you can have 11 as the sum. Now is it compatible? So let's figure out. So if you see, you are taking, in the best scenario, you are taking 3 edges where you have applied the operation. So in total you have applied the operation 3 times. That is, you have to apply the operation on this node, but the best scenario, and the best scenario says that I will get the best result if I apply the operation. So everything is compatible, so the value 11 is actually possible. But if it would have been different, let's say it is 3, in that case it will become 0 and 3. So you will say this is not compatible. Now I have to compromise on any one of these. Compromising on any one of these will make this compatible for sure, right? So I will then figure out the differences. So I will say this will give me a difference of 3. This will lose me 1. This will lose me 1. This will lose me 1, and this will lose me 1. So which of them is losing me the minimum is one I will take, right? So hope this entire approach is clear. Now this exact thing you can apply on a bigger tree and it will all still work, right? So let's just take one small example before we look at the pseudo code for this particular approach. So this is just the exact same thing, but we are applying this on a bigger tree. Now we are saying, okay, what is the maximum value here? So for that, you know what you need to find out. What is the maximum value of this subtree given I will take this node and I will not take this node. Similarly, you will figure out what is the maximum value of this subtree given I will take this edge or I will not take this edge. Similarly, what is the maximum value of this subtree given I will take this edge and I will not take this edge. So these are 3 independent sum problems. So you can call the same function. Let's say you are having a function of DFS where you are figuring out, okay, what is the maximum value starting at node 3 and given there is no change at all from the parent. So there is no parent for 3, so there can't be any change. So this will denote whether you have taken the parent edge or not, right? So you want, to calculate this, you want DFS of 0 comma true, similarly DFS of 0 comma false, and in the same fashion you want DFS of 1 comma 2, 1 comma false, DFS of 1 comma 2, 1 comma 2 and 1 comma false. So all of these you want before you can actually compute the value here, right? So basically all of these are exact same subproblem. So let's try to figure out the value for this node. So if you see, the value here again will depend what is the maximum value you can get from this subtree given I will take this node or I will don't take this node. Again, the value of k is still 3. So if you take this node, the value will become 1. If you don't take this node, the value will become 2. That's fine. Now the same thing you have to figure out for this subtree as well. So let's do this. So you have to figure out the value here given you don't take this edge or you take this edge, right? So let's first figure out the value when you take this edge. So if you take this edge, you want the maximum value of this entire subtree, right? So for this again you will say what is the maximum value when I take this edge, when I don't take this edge, and what is the maximum value when I take this edge and when I don't take this edge. So in this case it will become 1 comma 2, and for this one it will become 2 comma 1, right? Now what is the value here? So again, 2 things. If you either you will apply the operation or you don't apply the operation. If you apply the operation, it becomes 0, and if you don't apply, it will remain 3. Now what is the best scenario? Best scenario is 2, 2 and 3, so 7, right? Now is 7 possible? So the answer lies in the fact, let's see, you have taken this, you have taken this, and you have taken this. So if you take these two, here you are saying that I will apply the operation, here you are saying I will not apply the operation. So in total you are applying one operation. So this you have to apply the operation. So if you apply the operation, you will get 0, right? So this is not compatible, but you are also saying that I have to apply the operation for the parent edge as well. So basically there is one apply operation pending here. So for that apply operation you can actually get to this state as well, right? So in total you can apply an extra operation even though you may not have applied the operation from this children's, right? So you can get to 3 and hence 7 is possible. So you are saying that 7 is the value if I apply the operation here. Now in the same fashion, if you don't apply the operation, what is the value? Again you will figure out these two things anyways. So 1 comma 2 and 2 comma 1 will stay as it is. Now what is the maximum sum? 7, 2 comma 2 comma 3, 2 plus 2 plus 3 which is 7. Now is it feasible? The answer lies in the fact you how many operations you have applied? Only one, right? Only in this case you have applied the operation. So you have to apply the operation here. So if you apply the operation here, you will end up having 0, not 3. So but you want 3. Notice there was no operation from before, so now you can't actually skip this. So you have to apply the operation. So you can't go to 3. Now you have to now compromise on one of these. So let's see. If you compromise here, you will lose 1. If you compromise here, you will lose 1. And if you compromise here, you will lose 3. Which of these you will compromise? Answer is the minimum one, which is 1. So in total you will get 6. So 7 is the value you will get from this entire subtree given you take this node. 6 is the value you will get from this entire subtree given you don't take this node, right? This is what you want. So let's just get rid of all of this for having some space. For this one, again the value would be 2 comma 1 given you take this node and you don't take this node. Now for this one, it's very similar to this one. So let's say you are taking this node, right? So if you take this node, you now want what is the maximum value of this entire subtree. So for this you want what is the maximum value of this entire subtree given I take this node and I don't take this node. Similarly, what is the maximum value of this entire subtree given I take this edge or I don't take this edge. So in this case the value would become 1 comma 2, and for this one the value would become 0 comma 3, right? Because if you take this one, take this edge, this will become 0. If you don't take, it will remain 3. And for this one the value will become 1 comma 2 2 comma 1. If you apply the operation, this will become 2. If you don't apply, the value will remain same, which is 1. So in total you are having 2. The best case is 2 plus 3 plus 2, which is 7. Can you get the best case? So you are not applying the operation here, you are not applying the operation here, so you don't have any possibility of applying the operation here, so you will get 2 as well. So overall it is possible, but you have applied the operation here as well. So basically you have to apply operation on 1 or basically this here you have to apply operation or you have to cancel it with someone else, right? So in total you have to apply odd number of operations in total, but currently you are applying even number of operations. You are not applying even number of operations, rather you are actually applying odd number of operations because you have chosen this 1 to 2, which will make this 2. So in total this is possible, 7 is possible. So if you take this edge, the value will become 7. Now what about if you don't take this edge? So in this case you have to now apply even number of operations here. So in this case the maximum value is 7. Now if you don't take the maximum value, maximum value is not feasible first of all because you have applied even number of operations, so this will not change, and if it don't change, you have to go with 1. So you have to compromise on something. So which one of these you will compromise? Again the minimum one. So the one, if you compromise this, you will lose 3. If you compromise on this, you will lose 1. If you compromise on this you will lose 1. So in total 1 is the minimum compromise you can have, so that will be the one. If you don't take the edge, you will get a maximum sum of 1, right? So once you have figured out the values for each of these nodes, now you can assume these all things is not there at all, and instead you just have these 4 values. Now you can figure out the value of this one in the very same fashion. If you take this edge, the value will become 3. If you don't take, the value will remain 0. Now just take the maximum ones, 2, 7, 2, 7. So 14 and 4, 18, and then 3, 21. So in total you are getting 21. Let's see if it's feasible. Taking, and not taking. So in total you have taken 3 nodes or 3 edges here. So you have taken odd number of edges. So here you can actually have an operation. So you can actually take 3. So overall this is possible, but it's only the case when you don't take this edge. If you have taken this edge, then you have to actually account for one extra operation, in which case you have to optimize on something. So if you don't take this edge, the maximum value is 21. Now if you take this edge, then you have to, so if you take this edge, in this case you are saying that this will be changed, this will be changed to 3, right? In this case the value will change, this will become 0, this will become 3. So in that case you can actually, what you want is actually 3, that is you want to apply the operation, but here you are saying that you have not applied the operation, right? So in total you have to subtract something and you will subtract the minimum one to get this particular value, right? So you can do the exact same thing for all other things, and finally you will get the value here, right? So if anything is not clear, just rewind and watch the previous sections. I am very sure you will be able to understand this. So what is the pseudocode? The pseudocode will be exactly similar to what we have just done. So we have this simple function which takes two things, source and taken, whether the parent node is taken, that is whether we are modifying this node or not at all, right? So if parent node is taken, with that means that you are modifying this edge completely, right? Or modifying this value of this node completely. So that's what this taken will denote. Now here we have memoized this as well, because you have seen that when you are calculating the value when this node is taken and when this node is not taken, you actually need these two values again. So for that reason you might end up recalculating the values again and again. So it's better to keep track of what you have already calculated, and if you have calculated, just return it from here, right? So that you don't have to calculate the same thing again and again. Now we want to calculate this value, so we want three things. What is the best possible value? How many edges we have taken in this best possible value, or how many nodes we have flipped, and what is the minimum possible difference between best and non-best. So initially the value is val of src, and the other value possible is val of src is or k. So whatever is maximum, you will add it to the best, and similarly if you have taken the XOR one, you will simply increment your taken in best, and min non-best difference would become the difference between them, the absolute difference between them, because that's the one you will actually lose if you take the non-best one, right? You will do the same for all the children of source. You will figure out the best value with and best value without, right? After that you will simply keep on accumulating best and how many edges or how many nodes you have flipped in that best call, and what is the minimum non-best difference that you can have. Now after we have done all of these, taken in best will denote how many edges you have actually flipped or how many nodes you have actually flipped, and you will just do it modulus equals to 2. That means whether you have flipped odd number of edges or even number of edges. So if you have flipped odd number of edges, that means if you have flipped odd number of nodes or odd number of values, it means you can actually you can't actually take the current node, right? Because if you have flipped let's just take this example again. So let's say you have flipped this edge, this edge, this edge, but you don't have flipped this one. So you have flipped odd number of edges. So in that case you can't actually take the you have to actually flip this one as well. That is, you have to take 0 here instead of 3, right? So if you have flipped odd number of edges, you have to now like sacrifice some of one of the best ones so that it is feasible, right? Because at the end, if you apply the operation once, you will be flipping 2 nodes. So in total you will be flipping odd number even number of nodes at the end, right? So that's another way to optimize this, to visualize this. So at the end you want to flip even number of nodes only. So if you have flipped odd number of nodes, then you have to take the non-best version for one of them. So in this case, you also have this taken here that says whether to flip the current node or not. So if it is equals to this, that means how many you are allowed to flip, you have flipped only that much, then it is still possible to keep the best value with you. But if taken is 0 and taken in best is 1, that is you have flipped one more node than required, or vice versa, in that case you have to actually sacrifice the best one for one of them, and the minimum one you will sacrifice, and you will get the answer, right? So you will keep on doing this for all the edges, for all the nodes and for all the taken values, and finally you will get the answer. So what is the overall time complexity? You are doing something for each state exactly once, because if you encounter the same thing again, you will not do anything afterwards. So how many states you have? Total number of total different values of SRC, which is n, and the value of different value of taken, which is either true or false, which is true. So in total you have 2n number of states. For each state you are iterating over all the children's, and you are figuring out something with some mathematical operations. So overall you are iterating over all the edges for each node twice. So overall you will have a complexity of order 2n itself, right? So hope this entire solution makes sense. Now if you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself, because that's the best or the must part when you actually upsolve. So next we're looking at the code. The code is exactly what we discussed. We are figuring out the value of 0 comma false. So we routed the entire tree at node 0 ourselves. Any route is fine, because at the end we are trying to find out what is the best possible for the entire subtree. So any you can route the tree at any node, it is fine. So first we calculated the parent, and then we route the tree at 0 and just call the DFS with false, right? So parent calculation will just simply figure out the parent for every node. That's it. Why we need this, we'll come to that. Now in the DFS, what we are doing is the exact same thing we have done in the pseudo code. If it is already computed, we will return that as an answer. If it is not computed, I will figure out what is the best possible value, how many nodes we have flipped in that best possible value, and what is the minimum thing that I can give off in that configuration. So for the current node, I have calculated everything. Now afterwards I will go over all the children. Now here it's where the parent will require. You want to find out, you don't want to go to parent again, like you don't want to have an infinite loop. So if it is parent, you will continue again. Why this is coming? Because you have edges instead of the actual adjacency. You don't know, because you routed the tree at 0, you have to somehow figure out which node is actually the parent, because in the adjacency list of the child you will also have the parent, right? So after figuring out the child, you will go over all the child, figure out the with and without, and update the min, diff, best, and taken in best. At the end you will just do taken in best modulo by 2, which basically denotes how many nodes, or whether you are flipping the current node or not. So if that actually is equals to taken, then good, you can take the best value. Otherwise you have to sacrifice one of the best values, in which case you will sacrifice the one which will give you the minimum possible difference. So hope this entire session makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. So next, let's look at the second solution, is very interesting than this one. So basically we are trying to find out, or the basic approach here is, we know that after this operation we will be applying XOR k on some nodes, and we will not be applying XOR k on other nodes. So if there are n nodes, we may be applying XOR k on t number of nodes, and for other n minus t number of nodes we will not apply XOR k, right? That's the final configuration which we will have. Now we need to now figure out which of these nodes you will apply XOR k and which of these you will not. So like which of these you will tick and which of these will you not tick, right? So in total you again have in brute force manner you can have 2 power n combination and you can figure out the best one to get the answer. But the catch is, even to use this brute force manner approach, you first need to figure out, let's say you say, okay, I will take this and this. Is it even possible to only modify these two nodes without modifying anyone else? Is this configuration even possible, is the question. And if you are able to answer, if you're not able to answer this question, that 2 power n approach will anyways not work, right? So the problem statement with us now is, given a tree and given some set of nodes, is it possible that I touch only those nodes or apply operation on only those nodes while rest of the nodes will stay as it is? So answer in this case lies in the fact that the operation we are doing is actually XOR, and XOR, if you do twice, it will get back to the original state. So in this case, if you want to modify only these two nodes, what you can do, you can simply figure out the path from this node to this node. Because it is a tree, there is just one path, and in this path you can keep on applying the operation. You will apply the operation on this edge, in this case it will change. Now you apply the operation here, so because you apply the operation already, so this will remain as it is and this will change. You will apply the operation here because you have already applied here, so this will revert back to original state, this will change. Now you apply the operation finally on this edge, this will revert back to original state and this will change. So in total, at the end, only this node and this node is changing, rest are as it is, right? So you can do this for any combination and it will still work. So in essence, if you have chosen even number of nodes, then you can actually get to that combination without any issues. Notice the problem doesn't ask us to figure out what all operations you want to apply. Even if it asks, there is a good way to find out even in this approach, but currently it doesn't ask. So we don't care about which operations we are applying, we just care about whether it is possible to get to the configuration or not, right? So in this case, what we are saying is, if there are even number of ticks, then it is possible to get to the configuration. If there are odd number of ticks, then it is not possible to get to this configuration. So in this case, there are like 5 ticks. So we are saying that it is not possible to get to this configuration. Why? Because if you take these two nodes and go via their path and apply the operation, so these two nodes will be ticked, that's fine. Now you take, let's say, these two nodes, so you go via their path and apply the operation, so these two nodes are ticked. Now this node is remaining and this node doesn't have a corresponding partner with which you can go to the path and tick the node. Now if you apply the operation for this node, any one node should have to be ticked for sure. So basically, if there are odd number of nodes that you want to tick, it is not possible. But if there are even number of nodes that you want to tick, it is possible, right? Now what's the solution? The solution is, let's figure out which of these values are best with ticks and without ticks. So if you look at this value, or let's look at this tree, yeah, so everything is 7, right? And k is 3. Now if you do 7 XOR 3, you will have 4 with you, right? Now how many nodes are better with 4, or how many nodes are better with XOR k? Answer is 0, and because 0 is even, you can get the max of every node and you will get the answer, right? Let's take this example 1 to 1. So in this case, if you do XOR of 1 with 3, you will get 2. If you do XOR of 2 with 3, you will get 1. If you do XOR of 1 with 3, you will get 2. Now XOR was greater here, XOR was greater here. So in total, XOR is greater in 2 of the nodes, right? So because it is greater in 2 of the nodes, that means you have to tick 2 of them. And because you can take even number of nodes, then you can actually get the max value across all of them. So you will take the XORed one here, non-XORed one here, and XORed one here, and that is possible. Now let's assume that this was 3, right? And in that case, so the value is 1 2 3, and we have k equals to 3. Now in this case, if you do XOR here, this will become 2, this will become 1, and this will become 0. So XOR 1 is better here, non-XOR 1 is better here, non-XOR 1 is better here. So in total, XOR 1 is better in just one of them. So that means you have to take only one node, but that is not possible, right? So what you will do in this case? In this case, you have to either remove one XORed one, or you have to actually transfer one non-XORed one to a XORed one, right? So that's how you will make this even, right? Either you remove -1 or you will do +1. That's the only way to make this even. So in this case, you will do the exact same thing. Which one to actually do is you will figure out by how much you will lose. So in this case, if you change this one, you will lose 1. If you change this one, you will lose 1. If you change this one, you will lose 3. So which one of them is giving you the minimum loss is the one you will take. So in this case, the maximum value was 3 + 2 + 2, which is 7. You will lose minimum value, which is 1, and total value you can get is 6. 6 is the answer, right? So that's the greedy approach to solve this problem. I'm not showing the code. The code is very straightforward. You just have to figure out this XORed and non-XORed one, and just take the maximum, figure out how many of them is the XORed one. If it is even, that's good. If it's not even, just figure out the differences and take the one with the minimum difference to get the answer. So hope this solution is also clear. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.